Hello, dear students. I am Chaman Kumar from JNB Khwai, West Tripura. All right. Today we will discuss an important unit of your syllabus, which is work, power, and energy, and it is Unit 4. We will discuss some of the last portion of this Unit 4, which is conservative forces, the conservation of mechanical energy, and uh, the collisions. All right, these three things we'll be discussing, and in this video we will discuss what is conservative force. All right, we will understand the concept of conservative force, and this conservative force concept is very important, as in the coming classes also you will be using this concept. So you have to be very careful about this concept of conservative force. All right, so we will start this concept. All right, concept of conservative force. So before we get into the slides, let me explain what it is. All right, we know there are a number of forces, right? Okay, there are gravitational forces there, electrostatic forces there, magnetic forces there, nuclear forces there. So many forces are there, but on the basis of the amount of work done, these forces have been categorized into two groups. One is conservative forces, and the second one is your non-conservative forces. All right, so what is the basic difference between these two forces is the difference in the amount of work they do. All right, whenever a force is acting, some kind of work is done. All right, and this work done sometimes depends on the path the particle has covered or the body has covered, and sometimes it is independent of the path covered. All right, for an example, if you'll throw a body upward, okay, so the amount of work done during the process depends only on the height to which the ball is raised. Okay, if you want to throw a ball to some height, all right, so the amount of work done just depends on the height, the final point that the ball reaches. All right, so the amount of work we have done depended on the 2 points only: the point from we have thrown it and the point that it at the end reached. All right, it does not depend on the kind of path it traverses, whether it traverses a straight line path or it traverses a parabolic path. Okay, it doesn't matter. All right, so such kind of forces which don't depend on the path, all right, such forces are called conservative forces. Whereas a push or a simple pull or frictional forces, they do depend on the path for the amount of work done. All right, if I will suppose there are 2 points, all right, and I have to join them, I have to take one body to the other, okay, by dragging it. All right, means frictional force will come into play. The lesser will be the distance covered, lesser will be the frictional force. Okay, but if I'll cover a longer path, okay, to reach the same point, then the work done will be more in case of frictional force. So this is the difference between a conservative and a non-conservative force. Okay, so this is a literal explanation. Let's understand it mathematically, what conservative force is. Okay, let's go into the first slide. Well, this is what a conservative force will be discussing. All right, so the definition goes like this. All right, the definition of conservative force is something like this. All right, a force is conservative. A force is conservative if a force is conservative if the work done by the force in displacing a particle from one point to another is independent of the path followed by the particle and depends only on the end points. Okay, let's focus on this line once again. All right, what it says: a force is conservative if the work done by the force, all right, in displacing a particle from one point to another is independent of path followed by the particle and depends only on the endpoints. As I said, I have already given you an example, which is your gravitational force. All right, so suppose this is a conservative field. In this diagram you can see, all right, see this diagram. All right, suppose this is the field of a conservative force. Okay, suppose here some conservative force is acting. All right, field means I want to say some kind of conservative force is acting here. So I have taken 2 points here, A and B. All right, so look at this diagram. All right, I have taken 2 points, A and the point is B, and I have taken two paths, path 1 and path 2, to reach from A to B. All right. Suppose uh, the amount of work done in taking the point from A, taking the body from A to B is WAB. All right, like this, WAB along path 1. All right, and for this, suppose WAB along path 2. All right, if the force is conservative, according to the condition of conservative force, what happens? The forces will be equal. All right, because from the definition it says that, but it says that no matter what path the body takes, it will do the same amount of work. All right, as you can see here, the work done in moving a particle along path 1 is equal to the work done in taking along path 2. So both the path, okay, in both the paths, the work done will be same. The work done by the conservative force will be same. So if we'll express this concept in mathematical terms, what will happen? WAB along path 1 means the work done in taking the particle from point A to point B along the path 1 is equal to the work done by the particle, uh, work done by the force in taking the particle from A to B along path 2 is same. All right, these two forces, these two work done are equal. Now see this line, okay, WAB along path 2. All right, see this see the first diagram now. All right, suppose I will take the body from A to B along path 2, and now I will bring back the body from B to A along the path 2. Okay, suppose in this case, in taking the body from A to B through path 2, I have done 100 joule of work. All right, then in taking the body through the same path from B to A, negative of this work will be done. All right, means if I have done 100 joule of work here, then here the same 100 joule of work will be recovered, or the work done will be negative. All right, like this. So the work done in taking the body from A to B along path 2 is equal to negative of the work done in taking the body from B to A along path 2. So this is equation 2. All right, so from the above equations we can see that, okay, just a simple concept, there is nothing complicated here. Okay, the very simple thing, as the force is a conservative force, that is why the work done through the same, both the paths are same. Work done along path 1 is equal to work done along path 2, and this one is a mathematical implication. The work done in taking the body from A to B is obviously equal to the negative of the work done in taking the body from B to A. So from the above equations we get the work done along path 1 is equal to negative of the work done in taking the body from B to A along path 2. All right, now we'll get to a conclusion that WAB along path 1 plus WBA along path 2 is equal to 0. Okay, now focus on these 2 points, WAB along path 1 and WBA along path 2. Let's understand what does it say in the diagram. WAB along path 1, this means the work done in taking the body from A to B along path 1, means this one, A to B along path 1. And what does the second term say? It says that work done in bringing the body from B to A along path 2, means this one, from B to A along path 2, and the total work done is how much? It's 0. And look at this diagram, it is a closed path. All right, the particle has traversed from A to B, okay, and again from B to A through another path. So this total journey is a closed path. All right, so this here we can derive a conclusion that, so for a conservative force, the work done along a closed path is 0. All right, so this is an important conclusion. So if the force is a conservative one, then the total work done in a closed path is 0. All right, next we will see some examples of conservative forces. All right, see this. Okay, So here are three examples of conservative force: gravitational force, electrostatic force, and elastic force of a spring. These three are conservative forces. How they are conservative forces? Okay, we'll discuss one by one. Okay, look at this diagram on the left side. Okay, see this diagram. Okay, suppose I have got a body here. All right, this red one is a body, and I have to take to a height h, this much. All right, so there are a number of ways I can do so. All right, I can throw the body directly vertically upward, or I can take the body along this path as well. So no matter in which path I take this body to this height, at the end the amount of work done by the body, sorry, on the body will be how much? E is equal to mgh, which is its potential energy. All right, so it just depends on the height or the path. All right, it just depends on the final point, at what height the final point is. All right, so that is why it is independent of the path followed. So that is why gravitational force is a conservative force. Okay, and what more, one more condition of conservative force is there, which is called the work done in a closed path is zero. All right, suppose you know Mm, in taking the body from this point to this one, suppose mgh, this much of work is done, minus mgh. Why minus mgh? Because the acceleration is negative while going upward. So this much is the work done in taking the body from a point below to a point upward. All right, so in taking the body upward, this much is the work done. And when the same body returns to ground like this, okay, an apple, it was thrown and it comes back, while the upward journey the work done is negative, while the downward journey the work done is positive, and the total work done is zero. And this is the condition of a conservative force. So gravity force or the gravitational force is a conservative force. All right, similarly spring force. All right, so look at this diagram. All right, in compressing the spring, okay, in pushing it towards the fixed end, okay, the amount of work we do on the spring, okay, will be equal to the work done when we leave this body as it is. When it comes back to its original position, it also do the same amount of work, but in a different direction. All right, because the force is different. So this here also the total energy is zero. All right, so this is also an example of conservative force. All right, it means that the condition is what? The condition is the total work done during a closed path is zero. All right, so we have taken this body from this position towards the end, towards the fixed position. All right, and it came back again to the same position. And what is the total amount of work done? It is zero. So that is why spring force is also a conservative force. All right, now we'll see some kind of non-conservative forces. And what will be the definition of non-conservative forces? It will be very simple. If the amount of work done in moving a particle from one point to another depends on the path along which the body moves, then such a force is a non-conservative force. All right. If it depends on the path along which the body moves, then it is called a non-conservative force. Best example is your frictional force. All right, the force of viscosity, air resistance, push or pull, all these are your non-conservative forces. So why frictional force is a non-conservative force? All right, suppose we have got 2 points. All right, and I have to take one body from one point to the other point. Suppose I will cover this distance through a straight line. The amount of work done by this frictional force will be less than the amount of work done if I take the body in a car path, or by in an extra if I'll cover some extra path to reach the same point. So the work done will be different. Okay, so in case of frictional force, what happens? It depends on the distance the body covers, so that the work done is also becomes different. So that frictional force is not a conservative force, it is a non-conservative force. All right, so these are the non-conservative forces. At the end we will see some properties of conservative forces, okay, which is very important. Okay, so these are the properties of conservative forces. All right, and let's understand what are the properties. Okay, let me explain. The first one is, for a conservative force, the change in potential energy of the system is equal to the negative of the work done by the conservative force. For a conservative force, what happens? The change in potential energy of the system is equal to the negative of the work done by the conservative force. Okay, we will explain this mathematically. Okay, I've got a body here which is initially at a height h1. Okay, and I have taken this body to a height of h2. Okay, in this diagram you can see. Okay, so the initial potential energy of the body was how much? mgh1, and the final potential energy is how much? mgh2. So what is the change in potential energy in the body? It is mgh2 minus h1, obviously. All right, now what we have to see is, now let's find out what is the amount of work done by the gravitational force. What is the amount of work done by the gravitational force? We know that W, the amount of work done, is the product of force and displacement, is it? So force into the displacement, h2 minus h1. And why negative? Because this is an upward motion, so work done is negative. So minus of F into h2 minus h1. All right. Okay, now what will happen? This is, instead of F, we can put m into g, mass into gravity, minus mg, h2 minus h1. All right, now compare these two. Okay, here this is mg h2 minus h1, and this is negative of mg into h2 minus h1. So from these two we can derive that, the work done, the work done by the conservative force is equal to the negative of the potential energy, or the vice versa. All right, W is equal to mg h2 minus h1 is equal to change in potential energy of the system. All right, the negative of the work done is equal to the change in potential of the potential energy of the system, and this only happens when the force is a conservative force. All right, the second point is, the work done by a conservative force is path independent but depends on the end positions only, end points only. So these are path independent, but on what position they depend? That just depend on the initial and final positions. The work done along a closed path is zero, as we have discussed in the first slide. Okay, the work done along the closed path is zero. If only the conservative force acts, then the total mechanical energy of the system is conserved. Okay, in the next video we'll discuss about this, the conservation of mechanical energy. So for the time being, just remember that these four important properties of conservative force. What are they? One is, the change in potential energy of the system is equal to the negative of the work done. Okay, the work done by the conservative force is path independent and just depends on the endpoints. Third one is, the work done along a closed path is zero. All right, and the last one is, if only the conservative force acts, and the total mechanical energy of the system is conserved. Okay, so all these are the properties of conservative force. All right, so in this video we had discussed what do we mean by conservative force, what are its properties, and what are the examples of conservative force. Okay, and what are the conditions to be a conservative force. All right, so all these things we have discussed. We'll discuss in the next video the law of conservation of mechanical energy. All right, thank you.